Okay, good afternoon, ladies and gentlemen. Time here to start to this second lecture. I think we really should be talking about cycrophiles today. It's got me on cold. But it's actually halophiles. So I started doing them in yesterday's lecture. And just to remind you, these are the organisms we find in quite niche environments, in the sense that really high salt environments are fairly rare. So the natural ones, inland lakes like the Dead Sea and the Great Salt Lake, are examples of them. There's quite a few. There's a number of lakes in China and India as well, which are salt lakes and have been quite well studied. We have got the man-made, human-made evaporation ponds and saltons for production of salt. And then with things like the Haber-Saline microbial mats, and the idea that in salt mines there's been some very intriguing work done showing that possibly some of these halophilic bacteria can survive for possibly millions of years, but it is obviously a bit controversial. And then towards the end of yesterday's lecture, I got to the point of starting to explain how these organisms do this. So if you're going to grow in, say, 3 or 4 molar sodium chloride, you have to keep the balance of osmotic pressure. As a single-celled organism, you have to have the same amount of osmotic pressure or slightly more inside, so that water tends to move into the cell slightly. If you didn't react to an increase in salt concentration, then water would leave the cell would become dehydrated and obviously would die. And the two main mechanisms then, first of all, is the high salt-in mechanism. So sodium chloride is never accumulated to the same level, but you do get a set of organisms that actually accumulate potassium chloride. So basically they swap the cation for sodium for potassium. And Dr. Baker will say more in his lectures about why potassium is a more sort of friendly cation than sodium. So you do have some organisms that do high salt in, and they actually have to adapt to the very high levels of potassium chloride inside the cells, but it's never sodium chloride. The alternative that I'll talk about mainly today is the low salt in mechanism, where we replace the sodium chloride with something else, a small molecular weight organic compound. And the best example for all the undergraduate students is looking back to your first year when we did the Dinardiella glycerol experiment. So glycerol is a good example of a compatible solute. And I'll talk a bit about glycerol later on. So basically, low salt in means that you don't have to adapt the machinery of the cell. That's one of the key things. These compatible solutes, as the name suggests, are compatible with metabolism. If you're going to use the KCl method, then you do have to adapt the internal parts of the cell to cope with the high salt concentration. So, which types of organisms use the high salt in option? So they're basically found in 3 groups of halophilic prokaryotic cells. So the high salt one is much less widely spread than the low salt activity. And for a long time, when I was giving these lectures, this list actually only consisted of one, that is the top one, the Archaea order of the Halobacteriales. These were the classic bacteria, Archaea prokaryotic organisms that grew in the salt lakes, which used the high KCl. But then it was found that there was a bunch of anaerobic gram-positive bacteria, so not Archaea, they were actually bacteria by phylogenetic definition, the Haloanaerobiales. And these are also found in the salt lakes, but obviously in the sediments where there's anaerobic conditions. And then more recently, though, when I say recently, about 10 years ago now, in Spain, and they did a lot of work in some of the saltrums in southern Spain, and the group at Rodriguez Valera's group found this really unusual bacterium called Selenobacter rubor, It is a bacterium in the sense of, if you do the 16S sequencing, it's a bacterium, but it's obviously been involved in some lateral gene transfer, so that it actually has picked up some archaeal characteristics, and again does use the high KCl mechanism. So basically, because the high KCl mechanism requires a lot of changes to the cell, you're going to find these organisms, there are far fewer of them, as we'll see the list I'm going to show you for the low salt in a minute is much more extensive, and also they are very much restricted to stable environments. So saltons are very stable, salt lakes are very stable. You wouldn't find these organisms in a rock pool, for example, on the seashore where the salinity changes, because these organisms need a nice, high, stable salt environment. Okay, so which ones use the compatible solute method? So the other thing that has changed over the years is we thought the only archaea, the only sort of halophilic archaea used the high saltin mechanism, but in fact methanogenic archaea, this particular group, some of them are also sort of halophilic, and these ones actually utilize compatible solutes. So the idea that there used to be a differentiation between archaea and bacteria, for students 10 years ago it was much easier, frankly. You just had archaea, high salt, everything else low salt, is not true anymore. We now know there are archaea which use the low saltin mechanism. And there are also some of the halobacteriales that use it as well. So it was really annoying when it started happening from the point of view of teaching, because it really muddied the waters, if you like. So the alkylophilic members of the halobacteriales, the ones found in soda lakes that I mentioned in yesterday's lecture, they also use the low saltin mechanism. Then after that we've got all the big groups, the heterotrophic and phototrophic bacteria. Any of these organisms, which of course are a huge number of organisms that are halophilic or even halotolerant, they all use compatible solutes, as do all the cyanobacteria. So any cyanobacterium that is halophilic or halotolerant will use the low saltin mechanism, and all eukaryotic microorganisms like Dunaliella also use the compatible solute mechanism. So C, D, and E are very large groups. A and B are two specific niche groups, to make the point that there is not a big there's not this distinction anymore between the archaea and the bacteria and algae in terms of high salt against low salt. It's a bit more complicated. Excuse me. So what I'll do for the rest of this afternoon is to concentrate on the low saltin mechanism first of all, and talk about compatible solutes. That's why you've had a whole bunch of handouts today, because I want to show you the sort of breadth of compatible solutes that there are out there. Explain a bit about how they work, and certainly the range of compatible solutes and how it fits in taxonomically, because it is quite interesting that certain compatible solutes are found in certain groups of bacteria or eukaryotes, and also they are better and best compatible solutes. So there is actually a range of what compatible solute you use will actually say how high a salt concentration you can actually grow in. I'll explain that hopefully a bit more clearly as the lecture goes on. Okay, so compatible solutes, first thing to say about them is they also have the name osmolytes, which just purely for historical reasons I don't use, because I've always called them compatible solutes. If you see the word osmolytes, it's exactly the same thing. They're highly soluble. They have to be highly soluble because they're going to have to be concentrated in the cell to very high concentrations within the cell. And they are not charged. So they either are uncharged or they're Zwitter ionic, and that really nice word just means they've got a positive and a negative charge that balance each other out. So basically at physiological pH, at the pH you find within a cell, these compatible solutes are uncharged. Being charged seems to be not compatible with being a compatible solute. Okay, so let's have a look at handout 1 to begin with, actually. This is handout 1 and 2, but let's have a look at handout 1 to set the scene for the rest of the lecture. So So handout 1, you should have sort of 5 or 6 or 7 sort of diagrams of the key compatible solutes. So the first thing to say is the only ones that I really want you to remember in detail are glycerol, glycine betaine, and ectoine, hydroxyectoine. So numbers 1, 2, and 3 are the key ones that I'm really going to concentrate on. And these are the ones that I'd expect that you could actually show the formula for these particular compatible solutes. Glycerol, as we'll see, is one very commonly found in cyanobacteria. And then the second row, sucrose, trehalose, and 2-sulfo-trehalose are less good compatible solutes. And if I mean less good, I mean they don't support as high a salt concentration as the ones on the top row, particularly glycerol, glycine betaine, and ectoine. The 2-sulfo-trehalose is an unusual compound, and that is actually found often within the archaea organisms that utilise compatible solutes. So for that first bit of handout 1, the key bits are glycerol, glycine betaine, and ectoine, and to note really that glucosylglycerol is found within the cyanobacteria. So I think that's just all I've written on the slide. Is the key compatible solutes then are these 3.5, if you like, because ectoine and hydroxyectoine only differ by that one hydroxyl group on the top right-hand corner of the molecule. Okay, so I'll come back to handout 1 and handout 2 in a minute, but what I want to do really is to go through the properties of compatible solutes, and just in general, and to see what makes a compatible solute, what they actually do, and then I'll come back to some more of the detail of handouts 1 and 2. Okay, so the properties they have is that at low concentrations, they actually protect enzymes from high salt. So you can actually do experiments in vitro, in the lab, by extracting enzymes, or you can just buy a commercial enzyme from Sigma. And if you expose it to high salt without any compatible solutes present, the enzyme will almost always not work. If you put it into high salt in the presence of even quite low amounts, 20 millimolar, 50 millimolar of a compatible solute, you'll actually retain some activity of the enzyme. So in the initial period when you move a cell from low salt to high salt, some of the salt will actually enter the cell before the cell can react. The cell will react by immediately trying to either accumulate or synthesize compatible solutes. And as they start to do that, they'll have immediate protective effect, so the cell can actually carry on metabolizing and eventually push the sodium chloride back out of the cell. So that's it. So once you've got a high enough concentration of your compatible solute synthesized or accumulated from the medium, then they will actually exclude sodium chloride. So the sodium chloride may rise in the initial shock period, but then it will fall again afterwards to a low level, certainly below 100 millimolar, and probably in most cases below 50 millimolar for the sodium inside the cells. And instead you've got a very high concentration of the compatible solute. And the key thing then is that even at these very high concentrations of compatible solutes, they don't affect cell metabolism. So again, you can do the experiment where you take a commercial enzyme and you can actually add in 1 molar, 2 molar, 3 molar of things like glycerol and glycine betaine, and you'll see literally no effect on the enzyme activity. So that's why we call them compatible. They're compatible with enzyme activity and also with the structure of the cells. But number 1 there is very important, the fact they do start to work immediately, so that if you have this transition period where you've been quite happily a cell in a fairly low salt medium and suddenly you find yourself in a high salt medium, there's a chance to adapt as soon as you start producing the compatible solutes. And as I said a minute ago, this means that the cell machinery, so all the enzymes, ribosomes, internal membranes of eukaryotic cells, none of this has to be adapted. So for example, in Dunaliella, the algal undergraduate saw in the first year lab, all its enzymes are normal, all its internal sort of structures are normal. It's the glycerol that protects the cells at high salinity. So this means that if you can actually produce a compatible solute in high amounts, you don't have to change anything else within the cell. You don't have to make your enzymes be resistant to KCl that we'll hear about next week when I talk about the high salting mechanism. So that means you can grow in rock pools. If you're a Dunaliella or if you're another organism using this type of mechanism, because you can go up and down the salt concentration. So if the salt concentration goes up, if the sun, and believe it or not, the sun does sometimes shine in this part of the world. So a nice summer's day over in Filey in the Yorkshire coast, if the rock pools start to evaporate, the organisms in there can actually respond by producing compatible solutes. When the sea comes back in, they can then throw the compatible solutes back out again and carry on growing. So this low salting mechanism allows them flexibility to grow across a wide range of salt concentrations and salt concentrations that naturally change with the environment. But the really interesting thing when you start to look at this in more detail is the extent of the salt range that the organisms can survive does depend on the energetic cost of synthesizing the compatible solute. So it kind of makes sense. If you're going to grow in 4 molar salt, you're going to need a huge amount of compatible solute. So if it was a compatible solute that took a lot of ATP to produce, then the chances are that you'd grow very, very slowly in 4 molar sodium chloride. But if it was a compatible solute that is much less energetically expensive, then you can grow reasonably well at that high level. So you have to imagine any cell where it's photosynthetic or heterotrophic can generate a certain amount of energy, and that energy is partitioned between producing, in this case, compatible solutes and growing. So if they have to use too much energy for producing the compatible solutes, then growth will decrease to the point that they may actually stop growing altogether. So the actual cost of producing the compatible solute is extremely important. So how do we measure the cost, if you like, of a compatible solute? Well, it's done essentially in ATP equivalents. So the 3 cheapest compatible solutes are the 3 that I've already drawn your attention to, and that's likely the most important ones. So glycerol, for Dunaliella and other eukaryotic algae and fungi, is the cheapest of all, in the sense that only roughly 20 to 30 ATP equivalents per molecule are required to produce glycerol. The problem with glycerol, and the reason that it's not more widely used, is that glycerol is actually very permeable to cell membranes. So most cell membranes would actually not retain glycerol within the cell. So the algae and the fungi that utilize glycerol have changed their membrane in ways that we don't entirely understand, to be honest. They probably involve changes to the sterol composition of the membranes to stop glycerol leaking out of the cells. But if you actually had tried to use glycerol with a bacterial cell, it would simply leak out of the bacterial cell. So although it's cheap, it's only used by organisms that can actually retain it within the cell. Glycine, betaine and ectwine then are the next cheapest ones. They are used about 40 to 54 ATP equivalents per molecule, and that is why they are the other next best compatible solutes. So they allow growth to much higher levels than the other compatible solutes that I mentioned already on handout 1. Excuse me. And the range, this 20 to 30 and 40 to 54, is actually explained by the fact that the higher figure in each case is due to autotrophic conditions, and the lower figure is heterotrophic conditions. So if you're actually supplying the cells with a good carbon source, not forcing them to fix CO2, then they can utilize a lower amount of ATP, but under autotrophic conditions for the algae, there's going to be a higher level of ATP. Okay, if you look back to handout 1 again, then we can see now why we've picked out the top 3, glycerol, glycine, betaine and ectwine, because they are the cheapest compatible solutes in terms of ATP, so we now know that's why they are the ones that are the best. And the bottom figure in handout 1 just simply shows this, what I've actually put in writing on the sheet. So if you look at the bottom figure with these columns, white and dark columns. So glycerol has got the shortest columns, the lowest amounts of ATP equivalent. Then ectwene, glycine, butane, and they're making a slight difference in the pathway for glycine, butane, but don't worry about that. The point there is that all of them are below 60 ATP equivalents. And then if you go to glucosylglycerol, the one that's common in cyanobacteria, it's significantly higher, and sucrose and trehalose are much higher. So that little sort of figure explains why glycerol would be the best compatible solute if you could retain it within the cells, but for cells that can't retain glycerol, then ectwene and glycine butane are the next best compatible solutes because of the ATP equivalence. And of course, the other thing they can do, back onto the slides again, is they can actually avoid making it all together. So if there was actually glycine butane in the medium, if you add that into the medium, then clearly the cells would take it up, and they would avoid having to use de novo synthesis. So de novo synthesis simply means synthesizing a compatible solute either from CO2 in a photosynthetic organism or from, say, glucose being provided to a heterotrophic organism. But if you actually put the ectwene or glycine butane into the medium, then the cells will actually take it up in preference to making it, because it's much cheaper in terms of energy to take up the compatible solute than it is to make it. Another little twist in that we'll come to in a moment is that you can also take up precursors as well. So it doesn't actually have to be the final compatible solute. If they can take up a compound from the medium that will allow them to produce the compatible solute much more quickly, with less steps of enzymes, less enzyme steps available or necessary, then they'll do that as well. Cells will always try to take the path of least energy cost so they can grow more quickly. So what we'll do now then is look at how this is done essentially in the heterotrophic bacteria. So what we're thinking about here is the group of bacteria that are found, for example, in seawater or are found in some of the salt lakes. They are more moderate halophiles rather than extreme halophiles, and some of them will actually be halotolerant in the sense that although they can grow in 3 molar sodium chloride, if you actually measure the growth rates from 3 molar down to low salt, they'll actually do best in the low salt. But nonetheless, these organisms can still produce these compatible solutes. Okay, so before I go on to that section, I think I'd just like to look back onto handout 2. If we just pull that out, just it seems a good point now just to sort of summarise where we are with compatible solutes in general. And what handout 2 is a list of the major taxonomic groups with some sort of subdivisions, and then the compatible solutes detected, and a whole bunch of references which simply don't worry about that. I don't expect you. I'm not giving you the details of any of these references. I will give you specific ones as we go through. But if you look at the top, we've got the archaea at the top. So these alkylophilic archaea using this 2-sulfur trehalose, which is shown on handout 1. And then the anaerobic methanogens use things like glycine butane, but mainly they use beta amino acids or amino acids with acetylated subunits like N-acetyl-B lysine. So basically, apart from a little glycine butane, the archaea use unusual compatible solutes. They use ones that clearly they have developed, if you like, during evolution quite differently from the bacteria and the eukarya. So the key thing for the archaea there, just to remember, they use unusual compatible solutes, for example, the 2-sulfur trehalose. For the bacteria, also got a big long list there. So we've got, first of all, the photosynthetic bacteria, the cyanobacteria. And you've got glycine butane, which is the best compatible solute. So the halophilic cyanobacteria use glycine butane. The moderately halophilic cyanobacteria use glucosylglycerol, which is shown in handout 1. And then the ones that are only slightly halophiles utilise sucrose and trehalose. So that can be related back to handout 1 to these columns showing you the different levels of energetic use. And that exactly ties in with the fact that glycine betaine is most energetically favourable, followed by glucosylglycerol, followed by sucrose trehalose. And that then tells you it goes from halophile to moderately halophile to only slightly halophilic. Within the anoxygenic photosynthetic bacteria, we get mainly glycine betaine, looking down the next list, some ectoine, and I'll talk about these organisms in more detail. The heterotrophic aerobic ones, about halfway down, Halomonas is a very well-known organism that I'll talk about. And now we're seeing the ectoine, hydroxyectoine, starting to dominate things. And then finally you've got Selenovibrio casticola or casticola. That's a classic marine organism which also uses ectoine. And you've got glycine betaine and trehalose as well. And then down in the eukaryote cells we've got glycerol and one or two others. Dimethyl sulfonyl-propionate is found in some marine algae including seaweeds, and then the fungi and yeasts use glycerol or other polyols like arabitol and mannitol. So with all that in mind, I just want to give you a little bit of a history of how these things were found. So I've sort of given away the answer by going through handout 2, but that's not really the key reason here. I just wanted to take through how this was unravelled using these aerobic heterotrophic bacteria. So basically we're interested in organisms that would grow in high salt concentrations, but would also grow in quite low salt concentrations, often found in seawater. And good examples are this Selenovibrio casticola and Halomonas elongata. And Halomonas elongata in particular will grow from very low salt concentrations, millimolar salt, all the way up to nearly saturated sodium chloride. So it's an extremely halotolerant organism. Selenovibrio not quite as much, but certainly up to 2 or 3 molar. So of course these organisms were taken, they were growing in different salt concentrations, and using chemical tests and other tests, you extracted the cells and you measured the compatible solutes. It's fairly easy to measure compatible solutes in high salinity because they're produced in such large amounts that most modern techniques will actually measure them quite nicely. And all the initial experiments that were done with Halomonas and Selenovibrio showed glycine betaine was the compatible solute. So every time this was done, you found that in complex media they were producing glycine betaine. And that was fine, everybody was happy with that. Growing in high salt, in rich medium, things containing yeast extract in particular, so most rich medium are things like tryptone and yeast extract, LB medium, commonly used for growing E. coli. And this is just a way of making sure everything is present in the medium, all the amino acids, everything a cell can possibly want, you put into these rich complex media. But of course you can also grow cells on minimal media. A minimal medium will have a carbon source, a nitrogen source, a phosphorus source, and so on, but everything will be separate. And in a minimal medium you know exactly what is present, so you actually add everything in separately. It's much more time consuming. To make up a litre of LB medium would take you, literally 5 minutes or 10 minutes. To make up a 1 litre of an M9 minimal medium that we use regularly in the lab, certainly if you're starting from absolutely, the first time you're making it up, it could actually take you a couple of days to prepare all the stock solutions and get the media made up. Once you have all your stock solutions, it will only take half an hour or so the next time. But nevertheless, it takes much longer to make up the minimal medium. But it's important that you actually contrast what happens in rich medium with minimal medium. So in the rich medium, what we think was happening is that in yeast extract we have choline, one of the components of this, and you can actually show that choline is very easily converted into glycine betaine. So 2 enzymes working together will convert choline to glycine betaine. So what Halomonas and Selenovibrio were doing, if you gave them yeast extract, is they're taking up the choline and actually making the glycine betaine from the choline. So they weren't making it from de novo, they were actually taking the precursor from the medium and actually making it very straightforwardly. Okay, so we want to turn to the third of the handouts today. And just the top diagram we're interested in at the moment, which is just showing you the very simple pathway from choline to glycine betaine. There are two enzymes involved, but the glycine betaine aldehyde is fairly unstable, so it doesn't really exist for very long. So the choline goes to glycine betaine aldehyde, and then immediately is transformed into glycine betaine. But you can see it's a very straightforward pathway, not many steps in it. And so again will be the most energetically sort of cheapest way to produce glycine betaine. So I say everybody is still happy at this point. We've got cells growing in rich medium, high salt concentrations, they're growing well. So taking the choline and converting it into glycine betaine, and when we extract the cells, measure the chemical concentration, chemicals inside them, we find large amounts of glycine betaine. Okay. So, next thing we did, and we did actually do this in my lab as well, with Halomonas, we grew it in minimal medium. And lo and behold, it grew well, at high salinity, and so we extracted the cells, looked for the glycine betaine, and it wasn't there. So in minimal medium, the glycine betaine had completely disappeared, and we couldn't find any compatible salt. So lots of tests were done. They looked at some anhydrine tests, and anhydrine tests is for NH3 groups in amino acids, so looking for any type of amino acid might be there, any sort of carbohydrates, sucrose, trehalose. And this went on for quite a while actually, in real time, and everybody's really starting to be quite puzzled because the cells are growing well. I mean, they weren't just sickly, or they were growing perfectly happily in minimal medium at 2 molar or 3 molar sodium chloride, but we couldn't find any compatible solute. And yet we knew from the sort of logic that I've told you already in these lectures, there must be a compatible solute inside the cell. So this went on for a bit, and people were trying to work out what was going on, until a guy, Erwin Galinsky, working at the University of Bonn, used NMR. Now this is the days when NMR was actually quite a new technique. Now with Prof. Williamson and MBB and others, it's a very commonly used technique with our big NMR machines in the basement of the building. But this is now back in the 1990s, early 1990s, when it was a relatively new technique. And Erwin got hold of an NMR. He took a particular bacterium. He didn't actually take either Halomonas or Selena vibrio. He used this other bacterium, Ectothyroidospira, which is a photosynthetic bacterium from the Soda Lake. But what he found was that when he measured the compatible solutes inside Ectothyroidospira, he found ectwine. So ectwine that I just mentioned to you in handout 2 was the answer to this conundrum. And the reason that we couldn't find ectwine is it's actually a cyclic amino acid derivative. So it doesn't have any free NH3 bonds, so it's an anhydride negative. So when you tried all the sort of classic chemical tests, nothing was showing up. But as soon as you did the NMR, you pick up this great stonking signal for ectwine, because of course it is there in very large amounts. So it was missed simply because there was no amine group, so NH2, I think I was saying NH3, to react with the anhydrine. It was actually in a site, in a circle, that was actually making this anhydrine negative. So once Erwin had shown this, and we could actually see that ectwine was there, then of course everybody jumped on the bandwagon, as we always do. When somebody makes a breakthrough, sort of found the nearest NMR machine, begged to get a little bit of time on the machine to see if it was true for all these organisms, and indeed, essentially it is. So all these other organisms like Halomonas and Selena vibrio, they all produce ectwine. And interestingly, if you grow them in complex medium, again, go back to the LB medium, you can actually find ectwine is actually there as well. So it's not just glycine betaine, ectwine is produced under rich conditions, but we just didn't see it before. We're just totally focused on the glycine betaine. Okay, so rich medium, glycine betaine, minimal medium ectwine, but in actual fact, when you go back to the minimal medium, so the rich medium, now you know how to find the ectwine. Ectwine is there as well. So ectwine is actually always present in these organisms. But what happens is if you give them the rich medium and the choline, they'll take the easy option energetically, and they'll actually accumulate a lot of glycine betaine and downregulate the amount of ectwine, because the ectwine is more expensive to produce. But in the minimal medium, it's only ectwine. They don't produce any glycine betaine, because glycine betaine without the choline is more expensive to produce. So ectwine is less expensive, and it's actually a better, inverted commas, compatible solute. And one of the reasons for this is that ectwine is actually produced from the central amino acid pathways. So it is an amino acid derivative. So the way you actually get ectwine produced is to switch on 3 enzymes that will actually take from the central pathways of leading towards aspartic acid. You can then sort of siphon off, if you like, carbon to ectwine. So this all relates back to what is the most energetically easiest or most efficient way for the cells to produce these compatible solutes. And bear in mind, this is so important because they're producing a lot of these compatible solutes. So one thing maybe I should have said earlier on that I'll put in here is that if, for example, you've got 3 molar of sodium chloride outside the cell, which is not incredibly high salinity for these organisms, both the sodium and the chloride are osmotically active. So if you've got 3 molar sodium chloride outside, for betaine or ectwine you need approximately 6 molar inside. Now it's not exactly 2 times. Any physical chemist from down the hill in chemistry would be throwing things at me at the moment. But to a first approximation, you need roughly double the amount of the organic compatible solute to actually cover the 2 parts of the sodium chloride, the 2 ions in the sodium chloride. It's a little bit less actually because of other physical chemistry reasons that we don't need to go into. But the point is, you need a lot of compatible solute. If you're going up to 4 or 4.5 molar, you're getting up to 8, 9 molar of that sort of region. And although these cells are also very small, this is still a lot of compatible solute. So it's absolutely crucial that you produce your compatible solute in the most energetically efficient way. So back to handout 3, then, just to look at the couple of other things that are on here. The middle diagram is not to be remembered in any detail, but it's just to show you, and I hope you can just about see in this photocopy, that these little letters are B's and E's. So really, this is a joint NMR spectrum of ectwine and betaine, showing you that they actually do have different peaks. So you can identify ectwine and betaine in the same sample, and you can see, you can also quantify it as well. It's tricky to quantify things in NMR, but it is possible. And so you can work out the amounts of these compatible solutes as they change with the different conditions in the cell. And the bottom figure then is simply showing you the ectwine pathway. So you go from, you take aspartite beta semialdehyde is heading towards aspartic acid. So the sort of diaminobutyrate acetylase takes it out of the common pathways, produces this diaminobutyrate, and then N-acetyl diaminobutyrate, and then the cycle is complete. And so you can see ectwine again at the bottom. It's also on handout 1, and it's a zwitterion. So there's a minus and the CO minus, but there's a plus charge between the 2 NH groups, but there's no NH2 group, and that's why we kept missing ectwine. We just didn't see it because we assumed that we actually checked for any amino acid derivatives, but not for this unusual cyclic amino acid. And the same thing is always true of most compatible solutes, that the best ones are synthesized from central metabolic pathways, and that's why ectwine is so good, because it is actually coming directly from a central metabolic pathway leading to aspartic acid. Okay, so Halomonas is a really interesting organism. It grows really well, and we've done lots of interesting things with Halomonas. We've actually given it glycine betaine as the only carbon source. So if you put it into low salt and give it glycine betaine, everything is fine. It uses some of the glycine betaine as the compatible solute and utilises the rest for growth and synthesis. If you put it into 3 molar and give it only glycine betaine, the cells grow less well because they're left with this conundrum of they need to use some of the glycine betaine to support metabolism, but they need some to stay to be the compatible solute. They'll produce a little bit of ectine under these conditions as well, and you can really start to, if you want to annoy a bacterium, then you can just keep messing around with the amount of the carbon source you give it. And we just found the ways that they controlled the pathways. Again, always optimizing the amount of excuse me, the amount of energy that they utilise as best they can, but they need to they need a carbon source as well. So you really do give them a problem if the only carbon source is the compatible solute, and that does cause quite a few problems for cells. Okay, so as I mentioned on Friday, there's not an MBB 340 or 6040 lecture, because I've got a second year lecture just on that 1 week that I have to give. But what I've done is to sort of finish this bit of the course, I've put up on the MOL page, Blackboard page this morning, this review by these 2 Portuguese researchers. Milton da Costa is a very well-known person working on halophilic organisms, particularly in the prokaryotes. And it's not a mega long review. A couple of the things, the handout diagrams that I'll have taken for this review are very similar to it. So what I'd like you to do is just to read through that review before sort of next time, as it were, and just make a few notes. So just have a few notes at the end of the notes you've made today, saying a little bit more about compatible solutes, particularly in prokaryotic cells. Refer to handout 2 and just see where that fits in to handout 2. And he also mentions things about the unusual archaeal compatible solutes as well. So if you just do that and just add a few things into your notes, then that will then complete the part on low salt in halophiles. And next Monday, when we return, I'll actually then sort of talk about high salt in mechanism and show you that's a very different type of mechanism, in the sense that everything in the cell has to change, and that's going to be very interesting to also listen to Dr. Baker on the effect that high salt has on proteins. Okay, that's a good time to stop today. I'm very happy to leave it there. It seems to have stopped hailing outside, so we may actually manage to get somewhere dry. Okay, thank you.